Hi, good day. We are Group 1 and today we will be discussing about our video presentation for our data communications lecture. Our topic is block coding, cyclic redundancy, and CRC. Okay, so our members are Mr. RJ Lopez, Miss Ella Pablo, Mr. Gian Navarro, Mr. Ron Santos, and myself. My name is Jonna Rojas. So let's begin. So the first topic is error detection and correction. So a part of error detection is the Hamming distance. The Hamming distance is between two words, which is the number of different between the corresponding bits. So the Hamming distance was created by R.W. Hamming, which is made for error detection. So we have two pairs of Hamming. We have two pairs for Hamming distance. Okay, as you can see here. Let us find the Hamming distance between the two pairs of words. These are the words. Okay, so we just go to the paint. So the Hamming distance between 0, 0, 0, 1 is 2. And this is because, let me show you how. As you can see here, we are given two words, which is 0, 0, and 0, 1, 1. This is how I answer and to find the Hamming distance of two words. So writing down the two words to get the Hamming distance, I simply align it and check if there are similarities and differences between the two words. So as you can see, this is similar, and as you can see here, this is not. So what we conclude is the distance between the two words is 2, since there are two different bits for the two words. Since it is stated that the Hamming distance between two words is the number of the differences between the corresponding bits. As you can see, there are two differences for the given bits for the pair of two words. So same goes with number 2. The Hamming distance between 10101 and 1110 is 3, and this is because, again, writing down the pair of words. Okay. The given bits are 1010, 1010 101 and 11110. So let us check if how many differences and similarities but we will focus on the differences. So these are similar, these are not. Just check for the similar ones first. Okay, so the different ones are 0 1 0 1 and 1 0. So again, we can conclude that the distance for the Hamming is 3, since there are at least three differences for the set of bits. Okay. So, going back to our PowerPoint, the minimum Hamming distance is the distance between the smallest Hamming distance between all possible pair in a set of words, as I mentioned earlier. So again, finding the minimum Hamming distance of the coding scheme in table 10.1. The 10.1 table, which is not given in our current PowerPoint, but this is what it's written. The first one is 0 0 0 1 1. As you can see, there are two differences: the 0 0 and the 1 1. So the second one is 0 1 1 1 1 0. As you can see, two differences, so on and so forth. So we will conclude that the minimum is in this case is 2, since all of its the majority of the table, and I mean the majority of the coding scheme in the table 10.1 is 2, the Hamming distance difference. So finding the minimum Hamming distance of the coding scheme in table 10.2, again, which is not given in our PowerPoint, but this is what is written in the 10.2 table. Again, 5 zeros and a 0 1 0 1 1. I mean, aligning it, we will conclude that it has 3 differences. To give you a further background of it, let's just okay, so the given is here, which is 0 0 0 0 5 zeros. Okay, so 0 1 0 1 1. So let's just skip with the similarities and focus on the differences. So here's one difference, here's two difference, and here's the 3 difference. So there are 3 differences for this pairs of bit. So now we'll try this pair. We have 0 1 0 1 1. We have 1 0 1 0 1. So skipping the similarities and focusing on the differences. Let's just change the color. So we have one difference here, here, second one, third one, okay, and the fourth one. So we can conclude that this has a Hamming distance of 4. Okay, and we can do this also on the pairs of the given pairs of the coding scheme in table 10.2. 3 3 4 3. Now the d minimum, or the minimum distance for it is in this case is 3, since the majority of it is shown in the table 10.2 is 3. Okay, so to guarantee the detection of up to S errors in all cases, the minimum block Hamming distance in a block code must be d minimum is equal, which means S plus 1. So okay, so a minimum distance for an error detection S, which is an S error, occurs during a transmission. So the Hamming distance between the code is sent and received by the code word, which is the S. There are data words and code words. So the minimum distance between the valid code is S plus 1, as you can see here, so that the received code word does not match a valid code word. Uh, I mean, I mean, contemplating on the doesn't match a valid code word, the minimum S plus 1, so it wouldn't be the same with the code word. It needs to be different since we're looking for an error detection. So an example here is the minimum Hamming distance for our first code scheme 10.1 table is 2, as you can see in our earlier examples, which is 2. And this code guarantees detection of only a single error. A single error because if we're given 2 Hamming distances, we will have an output or a single error only. So if, and I mean, putting this into logic, if we have 4 Hamming distances, we have an input of 1 to 3 error. So an output of 1 to 3 error, I mean. So if we have a Hamming distance of 6, we will have an output error of 5 only. So there you go. If 2 errors occur, however, the received code word may match a valid code word and the errors are not detected. I mean, there is no error detection. So our second block code scheme in table 10.2 is d-min is equal to 3. To further explain more about this, this code can detect up to 2 errors. As I mentioned earlier, we see that when any of the valid code words is sent, 2 errors create a code word which is not in the table of valid code words. The receiver cannot be fooled, which means it cannot be changed. I mean, we can't I mean, the receiver could not I mean, if you received a valid code word which it's not in the table, we will have an error detection for it, which means the receiver cannot be fooled with this valid code word. So this is the representation of a concept for finding d-min. So you can see the radius going to the y, and this is the x, and this is the corrupted 0 to s errors, which is which are the errors that can be added through the code word, or which can be subtracted through the code word. This is also the representations of two territory of x and territory of y. So to guarantee correction of up to t errors in all cases, the minimum Hamming distance in the block code must be d-min is equal to 2t plus 1. So a code scheme has a Hamming distance of d-min is equal to 4. What is the error detection and correction of the capability? First question is, what is the error detection and correction? And what is the error detection? As I mentioned earlier, if you have a 3 Hamming distance, you will have an error detection of only 2. We will be, as I logically input how I answer 3 of a minimum distance of 3 and having an error detection of 2, I just simply minus 1 in my own understanding. So if we have a minimum distance of a Hamming distance of 4, the error detection should be 3, as you can see. S is equals to 3. This code guarantees the detection of up to 3 errors, just up to 3 errors, but it can correct up to 1 error, 1 to 3 error. So, and the correction capability of the scheme, it is wasted, since if you have an error detection, error correction, or if you detected any error, the capability of it's wasted because a error correction code needs to have an odd minimum distance of 3, 5, 7. If you were given a bit of 1011, you will come across in writing it as 1357 in order to answer it. So almost all block codes used today belongs to a subset called linear block code, which is a part of an error detection. A linear block code is a code in which the exclusive OR additions modulo 2 of 2 valid code words creates another valid code word. Simply, a linear block code corresponds with an XOR gate. an XOR gate which has an output of 0110 when when you get the output and the input. When you get A, B, and the output, you have 00, which is equals to 0, 01, which is equals to 1, 10, which is equals to 1, and 0, and 11, which is equals to 0. That is an XOR gate which we will be using in a linear block code. So in a linear block code, as I mentioned earlier, the exclusive OR XOR gate of any two valid code words creates another valid code word. So the scheme in table 10.1 is a linear block code because the result of XORing any code word with any other code word is a valid code word. For example, the XORing of the second and the third code words create the fourth one. Okay, so I have an example here, okay, for the XORing of a code word. Okay, here. So how did we end up if we have data words of 2 bits and we have code words of 3 bits? As you can see, this will contemplate to if we have 2 data bits, we have 4 bits. If you could contemplate that. So putting it here for us to understand better. Okay. So since we have data words of 2 bits, the scheme on table 10.1 is a linear block code because the result of XORing in any code word with any other code word is a valid code word. That is C. So 00, we need to XOR this. We need to figure out how to XOR this. So again, the output code for a XOR is 10110. We have 00, we have 01, whichever you want it first, 01, and 1, 1. So the data words is 0, 01 is 1, 10 is 1, 11 is 1. So we had successfully XORed this bit right here and successfully put it in the code words, which is a valid code word. Okay. So the scheme in table 10.2 is also a linear block code. We can create all 4 code words by XORing 2 other code words. Okay, so I have here an example. Here you go. So we have 2 code words. By XORing another 2 code words, we end up with 0. By XORing another 2 code words, we end up with, again, 1. XORing the same code word, we end up with 1. And XORing 2 code words, we end up with 0. Okay, let me just put it in paint so we could understand it more. Okay, just a moment. Okay, here. Okay, so it's stated here that we can create all 4 code words by XORing 2 other code words. Since we had XORed this 2 code words first, we can definitely XOR 2 more. This is equals to 0 by the XOR NAND gate table, XOR table. Sorry. So 0, 1, 0, 1, end up with 1, 1, 0. We will end up with 1 also. As you can see, guys, that we had been following the XOR all along, since we're just basically XORing the code words 1, 1, adding 1, 1 here, as you can see. XORing another 2 code words, we'll end up with 0. Basically going back to the XOR gate, just following the XOR gate, guys. Okay. So here's another question. For the last question, we have since in our first code table, which is shown earlier, 10.1, the number of 1 is the non-zero code words are 2, 2, and 2. So the minimum Hamming distance is dmin is equals to 2. I'll show you the table 10.1, which is being exampled in this slide. In our second code, the table 10.2 is the numbers of 3, 1s, which is in the non-zero code words are 3, 3, and 4. So in this code, we have dmin is equal to 3. So you can see majority wins. This is the 10.1 table. You can see it's all 2s. It's all 2s. It's 2 1s. So the next table we have we have a different answers for each of it, but since majority of it is 3 1s, we end up with this case having 3 as the Hamming distance. So that would be all. My colleague will be discussing about simple parity check. Thank you.